Colloquium today, and today our speaker is Andreas Papaefstathiou from Kennesaw State University. And he's an expert on particle physics, and in particular particle tools and standard model and Young's model tools. And let me briefly introduce Andreas' background. So he got his PhD from Cambridge University with Brian Weber. And that's where I think you started developing expertise in code, which is an essential multi-color tool to do studies. And later he had done a postdoc at CERN, the Large Hadron Collider place, and Nick had Amsterdam and Edinburgh before he moved to Atlanta to professor in Kennesaw State University. And today, Andreas is going to talk about his research in particle physics and relations.
Thank you very much, and thanks for the invitation to be here. Okay, so the title is a little bit grand, but I'm actually going to start from the very beginning of my field. I know most of you are not working in the field of high energy physics, so I wanted to give an introduction to the field itself. I try to connect it to what I'm working on. So this is basically a representation of the title as generated by an AI with some additional prompts. So, this is Imprints of Electro-Weak symmetry breaking at colliders with a white background or something like that, abstract art. So this is what I got in this table called. Okay, so let me just mention, I have this little QR code, which is the PDF of the talk. If you want to have a look at it, and ask me a question later on, so you can do that. It's about 100 megabytes, so it might take a couple of minutes depending on your connection. So that this QR code will appear on the following slides as well. So in case you miss it now. Okay, so I skipped the zero slide, but anyway, here's today's plan. So as I promised you, I'll give you an introduction to the field of high energy physics. I'll discuss then some open questions that I am interested in, and then I'm going to discuss how they may be connected to a mechanism which is breaking a symmetry of our theory, and then I'll discuss one of the things I'm interested in, which is extended scalar sectors. I'll discuss these towards the end. And please, if you have any questions, feel free to interrupt me. Okay, so let's say the first thing is, what is high energy physics? So this is my view, of course. Other people might have a slightly different view, but let's say my view of the goal is that in high energy physics we smash particles together to emulate conditions closer to the Big Bang, and I call this particle archaeology in some sense, because we're trying to figure out what was happening in the past through these experiments. The other thing we do is, we smash particles again to understand the structure of matter today, and I call this particle sociology in some sense. So what do I mean by understanding the structure of matter today? Well, understanding what particles nature comprises of, and how they interact with each other. And okay, this is a nice graph showing what is called the standard model of particle physics. So these are the known particles. I won't go into the details of these. Let me just mention at the center lies this Higgs boson that I'll be discussing later on. So understanding the interactions of the known particles is definitely something that we're interested in, but also discovering exotic phenomena. So is there anything beyond this that we haven't seen so far? That's definitely something that we are interested in the field of high energy physics. Okay, so I want to discuss a rule that basically guides why go to high energy. Well, going to high energy allows us to probe smaller scales. So this is just, let's say, a fun diagram with various scales, and then with various objects at different scales. And if I zoom in onto the proton, the mass of the proton is 1 giga electron volt. That's, let's say, our favorite unit. And So to probe the structure of the proton, we have to go to energies that are much higher than this. So that's what particle colliders aim to do. And this is, let's say, one that is, well, this is the highest energy one, the Large Hadron Collider at the European Organization for Nuclear Research at CERN, which is in Geneva. And this is basically a picture of where the ring is on the ground. So the center of mass energy is 13,600 gigaelectron volts. So that's like about 14,000 times the mass of the proton. So this collider is made to go very deep into the proton and probe its structure. Okay, this is the ring, and I just wanted to show you a couple of other pictures of how that looks like. This is basically the tunnel, and I wanted to show you an animation, let's say a very rough animation of what's happening. This is a detector, so particles are accelerated in that tunnel that I showed you, and then they meet here and they smash onto each other in this way. So these are, let's say, two protons, and they collide, and then something happens. So before I describe that part of that collision, I wanted to give you some fun facts, to impress your friends and colleagues. So it has a circumference of 27 kilometers, and I also try to be inclusive with units. So I apologize for the miles and feet, but I think maybe I don't have a good feel for miles, maybe for miles I do, but for feet not really. So it lies. So this tunnel that I showed you is 100 meters underground to shield it from radiation that comes from outside, cosmic radiation, for example. And it produces hundreds of millions of particle collisions. So I will refer, I just wanted to define this. A collision I will refer to as an event. Okay, so sometimes I will say event instead of collision. I just wanted to make sure that we are speaking the same language. So the energy stored in a particle beam, so that's all the protons that are being accelerated at the same time, is about the energy of a 1,000 kilogram car at 3,000 kilometers per hour. Okay, I asked my physics 2 class to do this calculation as an exercise for understanding what an electron volt is. So you can try this about 1,900 miles per hour. And in case you're wondering how much data is being recorded, it's about 100,000 DVDs. And I now realize that DVD is probably not something we see every day. It's about 5 gigabytes, I think. It's between 4 point something and 8 gigabytes per DVD, so you can convert that. Okay, so let's go back to what's happening at the LHC. So I wanted to show you a real event. Okay, so here's again this collider, and then there's one beam coming in, the other one, and then this is one collision. So you can see the cross section of this detector. So this is a complicated array of let's say detector elements, and you can see various layers of the detector, and then these are the tracks that are made by particles that are moving the detector. So the question is, and the one that I'm interested in, how do we make sense of this kind of very complex event? And okay, on the one side we have some theoretical framework. I'm not going to go into the details of what that equation means, but we have let's say a theoretical framework. And on the other side we have the experiment, and the question is, how do we connect, the theoretical, the theory with what we see in the experiment? So Richard Feynman said, "Shut up and calculate," and that's one thing that we can do. And I wanted to describe the theoretical framework. I mean, very briefly, the theoretical framework that is being used. So it is called quantum field theory, and it is based on the two pillars of modern physics. The first one is quantum mechanics, which is what we use to describe the very small objects, right? Particles and so on. So if you're familiar with quantum mechanics, basically the object that we calculate is called a wave function, and is denoted by this capital psi. So we calculate the wave function, and then we basically take the square, the norm of the norm square of the wave function, and that is the probability to find the particle somewhere. Okay. The other part of quantum field theory is special relativity, and that is the theory of very fast moving objects. And we all know, even non-physicists know this equation, the energy and mass equivalent. So what does it tell us? It tells us that mass and energy are equivalent, and then that basically, what does that mean? It means you can convert energy into mass, but what does that mean in terms of particles? It means you can create particles and annihilate particles. So you can create particles from energy. So if you put the two theories together, the theory of the very small and the very fast, you get approximately something that is quantum field theory. And I like to imagine it, let's say, as a kind of field, where you can disturb one, like let's say 1 point, and then something propagates. So it's like basically a medium in which particles are created and destroyed. So, for example, if you consider an electron, it will correspond to a field. And then this field the electrons will be, let's say, disturbances in this field, in some sense. Okay, so how do we go from theory to experiment and back again? So let me sort of be a little bit schematic again. Let's consider a very simple interaction, and this is the interaction between two electrons. Okay, so we have two electrons. What is the simplest thing they can do? Well, it's just nothing, right? They don't interact. Let's say this is a zero order thing they can do. But we know, of course, that electrons can interact. They interact via the electromagnetic force. And let me just specify, of course, that as the animation showed, this direction will be time in some sense. So how do they interact? They interact by exchanging a particle which corresponds to the electromagnetic force, which is a photon. Of course, the photons and electrons interact, so you can have this electron emitting, as an example, emitting a photon. So if I now, I'm telling you what the outcome, what this looks like in terms of theory. If I now ask you, okay, don't worry too much about the expression, just focus on the fact that there is a C in front of the interaction between two electrons and a photon. So this is an electron emitting a photon, and it continues being an electron. So there is, every time you have such an interaction, you associate it with that C, which is a coupling. So every time I see a photon being emitted, let's say from an electron, I add basically a coupling to that. I associate it with a coupling. So I can, start drawing such diagrams. So I'm drawing, let's say, the first order diagram, and then I'm associating that with a C on each of the two interactions, and then basically what I am claiming here is that there is an object equivalent to the wave function in quantum mechanics, which is now proportional to C squared. Okay, so the product of each of the couplings. Now, if you do the same kind of thing for the other diagram, such as this one, then you see this one has 3 C, so this will be proportional. The wave function is not really a wave function, but the equivalent object, unequivalent object, is proportional to C to the power 3. And then if I imagine another diagram which has 4 vertices, then this one would be proportional to C to the power 4. So of course you can start drawing, various diagrams, and these are not the whole story. But what I'm claiming here is that you can calculate some object that looks like a wave function, and then you can square it to relate the appearance of each of these diagrams with a probability in a sort of similar way that you do with quantum mechanics. So I just basically squared those diagrams. So you can then ask the question, okay, what is the total probability of these kind of interactions between two electrons? So then you sum up over all of these diagrams. And the nice thing is, if this C squared, for example, is less than 1, then you can say, okay, I add all the diagrams that correspond to C to the 4, C to the 6, 6 to the 8, but then I stop here, and I have, maybe a good description of what I'm trying to calculate. So you can truncate that expression if C is well, C squared is less than 1. So we have a way of calculating probabilities in quantum field theory. Of course, in reality, this wave function or the equivalent object depends on the energy and momentum of the particles involved. So it's not, it's not just a constant, of course. There's momenta involved in there. So imagine there's an interaction somewhere, then 2 electrons come out of it. Then this psi will be a function of the energy and directions and so on, each of the electrons. Okay, so I'm just, very sort of broadly trying to convince you that we have a way to describe what we observe at experiments. Okay, so maybe you can say, okay, give me a piece of paper and I can calculate probabilities. However, it's not possible to do this on paper, and there's basically 2 reasons. So, okay, in principle, you can truncate this series, but if you go, if I ask you what is, let's say, the next term, it becomes, the number of diagrams you can draw becomes more and more, grows really fast, so it becomes very difficult to calculate additional terms in this series. The other problem is, I mentioned that you can only truncate this series if C squared is less than 1, but sometimes this equation, is not valid anymore because C squared is, this truncation is not valid because C squared becomes greater than 1 or equal or close to 1. So what is the solution? Well, you can basically consider many of these terms approximately. So this is one thing we do. And when you reach a point where you need to consider situations where C squared is greater than or equal to 1, you use models, right? Okay, so I'm not going to be very specific of what these are, but these are the solutions to these problems. So when you start doing this, however, you cannot work on pen and paper anymore. You need to use computers. And my claim here is that Monte Carlo simulations accomplish this. So they accomplish basically calculating the problem. They solve the problem of calculating probabilities in quantum field theory using approximations for higher orders and modeling situations where these couplings become larger than or equal to 1. So it's called Monte Carlo because of the casino in the famous casino in Monaco, Casino Monte Carlo. And the reason is that the Monte Carlo method in general is based on randomness and probability, which is also nice because it looks a bit like quantum mechanics. But that's another nice feature. So let me go back to this picture and this interaction between theory and experiment. And I claim that one of the main ways to interact, back and forth is through simulations. So the answer would be shut up and simulate instead of calculate. Okay, so I wanted to let's say, give you a flavor. You already are probably familiar with one of the simplest simulations, Monte Carlo simulations. And I'll just describe one, which is how to calculate pi. So this is a very simple simulation. You can write it probably on your computer very quickly. So what is the theory element in this? We all know the theory element from school. The first is that the area of a circle is proportional to r squared. And our goal, of course, is to calculate the proportionality constant pi, right? So, okay, this is, let's say, one element of theory. The other element of theory is that the distance, so if I draw this circle with its center on the xy plane, with its origin on the xy plane, then the distance of any point from the origin is simply given by the Pythagorean theorem, right? So let's say d squared is x squared plus y squared. So if I now enclose a circle in a square, so imagine this circle has a radius r, so the square would have radius 2r. And I ask you, if I pick a random point in this square, what is the chance that it will fall inside the circle? It will be the area of the circle divided by the area of the square, right? That's what we expect. So this is our theoretical component. So then our simulation is basically to pick random points uniformly inside the square and count the fraction falling inside the circle. So you pick a certain number of points, n, okay, and I'm going to show you how that looks like. So we claim that this probability is now pi over 4. So if I pick a certain number of points and I measure how many of them, I will get a better approximation. The more points I get, the better the approximation will be towards that probability. So let's see what happens. So I pick, okay, 10. So you see, if you actually, so and this is the only case we can actually count them. So you see there's 4 of them. The blue points are the ones that are outside. So you see there's 4 out of 10 outside. So you would get 6 over 10 times 4 to get pi. So that gives you 2.4. But now, okay, now of course you cannot count anymore. But you can see you get about 304 with 100, and then you get 308. Okay, and I also give you an estimate of the error, and then 3.13, and then okay, it starts to get closer, and this is really pretty good. Okay, so this is a Monte Carlo approach to calculating pi. So let me connect that with what's happening for particle collisions. So the theory component is, for example, the set of known particles and their interactions. So the standard model could be your theoretical input. We calculate probabilities via quantum field theory. So actually now I'm going to switch. Okay, I'm not going to use this very much, but this object that I call the wave function is actually called matrix element. So in quantum field theory. So what is the simulation? We pick n basically points in the space of the allowed constraints, and that could be the energy, there's energy conservation and momentum conservation and so on, and we can calculate the probability for each of these points. So that's already giving, that's basically the how Monte Carlo simulations work in particle physics. So what you end up is a list of particles that look like real events. So you get basically event number 1, momentum of each particle. So you get basically, imagine if the event is just the 2 electrons being created, then you will get the momenta of each of the electrons. And that would be one event, and then you get another one, another one, another one. So, okay, by the way, I just added this, that you can actually look how, if you want to construct your own Monte Carlo event generator, there was a little tutorial I wrote a few years ago where you can do that. Okay, so once you have lists of particles, this would be a theoretical prediction through the simulation. What can you do with it? Well, you can come back and do the experiment. And so I'm just showing you here some so this is a histogram of some observable that is related to the electron energy in some specific processes. We don't want to go into the details of this. So the data is basically the black little dots. And you can compare the data with predictions, and the predictions are the solid histograms. So the white solid histogram is actually a prediction through a Monte Carlo event generator. So yeah, so this is basically the sum of those 3 are theoretical predictions through simulations. Okay, so this is, let's say, simulating a known process and comparing it to what you see in experiment. But you can also take your theory and add a new particle to it. Okay, so here I'm showing you, okay, some observable quantity. I didn't want to describe it, but imagine we have some variable that we can measure very well at the collider. So if you look at this plot, the stuff that I circled in green is the simulation of the stuff that we know exists, and the red histogram is something that I added to my theory as a new particle. So the black dots, that hopefully you can see, are basically the experiment. So you can now, okay, you have to do a statistical comparison, but you can already, by eye see that this red histogram is unlikely to be compatible with reality, right? The red histogram is far beyond the black data points. So, so the hypothetical particle is not likely to be there, given my experimental results. Okay. So, okay, this is what we do. This is a way to determine whether a hypothetical particle is compatible with data. Okay, so you can do this you can do sort of both kinds of exercises for various processes, and I'm showing you here a collection of the standard model total production cross-section measurements. The cross-section, we don't have to know what it is just telling us how frequently an event can occur at a collider. So you see here, this is the frequency of the type of event, and this is the type of event. Okay, and this is a comparison between theory. So the gray lines are theoretical lines. Hopefully you can see them, but anyway, there's not much separation between the theoretical lines and the experimental measurements, which are the colored little rectangles. So you can see basically that they lie on top of each other for these processes, and the frequency variation between these processes is 13 orders of magnitude. So it's a really good result for the measurements, right, and versus theory. And I just wanted to emphasize that the Higgs boson that was discovered just over 10 years ago is already very well, any process that involves a Higgs boson is already very well measured. Okay, so I just wanted to zoom into that, and this is an extraordinary result, let's say, only 10 years after the discovery of a particle. So all of these processes are related to stuff that we know. What about searches for new phenomena? So this, okay, again, the details are not important, but basically these lines, these bars tell us what the minimum mass of a particle can be, of a hypothetical particle can be. And I just wanted to highlight that we haven't found anything recently, and the limits are from 1 tera-electron volt to 10 tera-electron volt. So 1 tera-electron volt is 1,000 giga-electron volt. So that you can, a proton is 1 giga-electron volt. So this is from 1,000 to 10,000 times the mass of the proton. Particles have to be heavier than that if they exist, given one of those theories. So the next, perhaps you might say, oh, there's nothing new, right? I mean, there's no new phenomena, and this is just this is an old picture I took from a hand-drawn. It was something hand-drawn that I found at an office in CERN, and it says the cemetery of physics is full of wonderful effects. But optimistically, it says that very often lead to theoretical and experimental progress. Okay, so maybe it wasn't so pessimistic. So, well, is that all? Or if that was the case, I probably wouldn't be here. And there are many questions that remain, and I want to focus on some of them without, many answers. I'm not going to give you answers, of course. And I just wanted to highlight that even the cat is a little bit shocked by the lack of answers to these questions. So I want to focus on some of my favorite questions, because I think that there is some relation. Well, there could be some relation between them. So the first one is maybe rather grand. What is the ultimate fate of our universe? And when I say that, I mean, what is the ultimate phase of the vacuum of our universe? So I'm going to discuss the Higgs potential in a second, a little bit in more detail. But imagine we have a potential which is basically, which is valid everywhere in space. And this phi is a field which fills all of space and has to respond to that potential. Okay, so at the moment, we know that we lie somewhere here near the origin, and we know a little bit about the shape around here, not everything. The question is, what happens when you go to high values of this field, right? So if you excite, this is a field that is basically possible to be excited everywhere in space. It's a Higgs field. So how does this potential look like? So it could be that it looks like the red curve. So the minimum that we are in right now, so we're in this minimum, could be the absolute minimum of the theory. However, it could be that there is another minimum somewhere else. And what does that imply? It implies that the field can go from the current minimum to that minimum. However, okay, this is something I'll discuss in a second. The fact that we are here determines a lot of things about how the universe works. And when I say that, I mean the masses of particles, and therefore chemistry and perhaps life. It depends on the fact that we are here. So if we have tunneling, that means masses of particles will change. Who knows what will be the case? And there are indications that we are in a metastable situation, and it's interesting to know why and to understand it. So it's a problem intricately related to the Higgs field. And this is known as the vacuum stability problem. Okay, so another problem is, why does the matter we are made of exist? So we know that each particle, well, most particles have an antiparticle. So that's basically, particles are matter and antiparticles are antimatter. But basically, most of the things that we're made of are matter, so they're particles instead of antiparticles. So why is that the case? Because, I mean, it's a puzzling situation because, for example, the electromagnetic interaction doesn't care whether you're going from a photon to an electron and a positron or the other way around. So it treats matter and antimatter on equal footing. And most of the standard model actually has this property, most of the stuff that we know. So why is it the case that we end up with so much more matter than antimatter in the universe? And this is called the matter-antimatter symmetry. The last one that I won't discuss in detail here, but I'll just hint of how it could be connected to this story, is related to dark matter. And one way that we know that it exists is through the rotational curve, so the velocity of stars around the galactic center of a typical spiral galaxy. So we expect it to drop off as this dashed blue curve, but however, we observe the red curve, the B curve, which basically tells us that the galaxies are embedded in some unknown form of matter that only interacts, or primarily interacts gravitationally with the known matter, with the matter that we know of. Okay, I just wanted to emphasize that this is a limited set of questions, and there are many more questions that we need to understand in physics. I'm going to focus on these three in some sense, because I think there is a connection. So the vacuum stability, dark matter, and matter-antimatter asymmetry could be connected through the Higgs field and the mechanism of symmetry breaking that I'm going to discuss in a second. And furthermore, these can be linked, but we also may have the chance, at least within the 21st century, to figure out whether models that can solve them are there or not, because there will be some experiments potentially, such as a future circular collider, which is a bigger ring, let's say foreseen around near the LHC, which could collide protons at much higher energy. So this is 100 tera-electron volts versus 13.6 that we have now at the LHC, or electron-positron collisions at various energies. We also have the possibility of a higher energy version of the LHC, or even a muon collider. So, okay, I'm not going to discuss the colliders themselves, but there are collider experiments that we are thinking about that could address these questions. Okay, so I promised I will discuss symmetry breaking. So I wanted to now go focus on this Higgs field and try to give you a flavor of how this works. Okay, so the field of the Higgs, as I mentioned, is basically you can imagine it as filling up all of space. So it's this phi. So it's a complex doublet, which basically means you can write it in that way. So phi has like these components. There's two complex numbers basically arranged in that form. Of course, I cannot display four-dimensional objects on the screen, so I just set phi 3 and phi 4 to 0 arbitrarily, and I now plot the value of the potential in which this field lies in on the phi 1, phi 2 plane. So it's, let's say, so I can show you a three-dimensional plot. So let's focus on the minimum. I probably need to go back again. So this is the possible evolution of this potential from the early universe to our day to day. So let's start this again. So in the early universe, this potential looks like a ball, and it has a minimum at the origin. So that means that everywhere in space, the Higgs field has to respond to this potential, it has to lie on the minimum. So this minimum is at 0, 0, let's say, phi 1, phi 2. So as, let's say, the universe cools down, what will happen is the following. I'm going to show like a little bit a one-dimensional version of this. But you see what happens is the minimum at the origin disappears, and what we end up with is a set of minima, and this is called the Mexican hat potential because it looks a bit like a Mexican hat. You have a peak in the center, and then you have like a set of degenerate minima. So they're all at the same depth, and so they're degenerate. Okay, so let me now show you a little bit. This was let's say, an animation. Let me show you, let's say, a one-dimensional example. And this is basically this is a cross-section of that potential. So how does that look like? It looks like a term which is squared in phi, so squared in the Higgs field, and there's a quartic term. Okay, so the coefficients are these blobs, circle and square. I don't want to write symbols. So again, going from the early universe, you have this symmetric situation. So this phi with brackets equals 0 means the average value of the Higgs field everywhere in space should be 0 because that's what the potential for it is. And today, however, we know that we are here. So the Higgs field lies at a minimum which is far away from the origin. And this phi, which is called the vacuum expectation value, is non-zero. So we went from something that looks very symmetric, the ball, is symmetric about let's say the vertical axis, to something that looks less symmetric. But it's just the fact that the symmetry is still there, it's just less obvious. So in order to do physics in this broken phase today, I have to go to the minimum and do little expansions of the field around the minimum. So how does that look like? Well, we have to take that potential, plug in the minimum plus some deviation from the minimum, and that deviation is going to be called h. Okay, so I'm going to plug in phi with the brackets plus h into that, and just expand it, and I get something like this. And basically, if you work with this kind of minimum, then you're doing physics around the minimum, and you're doing physics with h instead of phi. And that h is the Higgs boson, is the physical scalar that we discovered at the LHC in 2012. And okay, I just wanted to highlight that this is how a lot of particles gain mass. Okay, so you start off, okay, I'm not going to go into the details, but you have psi, phi, psi, and once you do an expansion, you get constant times psi, and that is a mass term. Okay, but if you don't know about that, then that's fine. I'm not going to focus on that. It's just an aside. Okay, so this transition from the symmetric early universe state to the state today is called the electro-weak phase transition. So if you see EWPT, this is what I mean. So before I continue, I just wanted to mention that focus on this potential for the Higgs boson for a second, so that this is the Higgs boson's potential. So this V corresponds to a quadratic term, a cubic term, and a quartic term. So these basically terms represent the self-interaction terms of the Higgs boson. So it tells you how a Higgs boson interacts with itself. So if you want to determine the shape of the potential, you have to be able to measure those. So how do you do that? Let's say you want to measure the quadratic term, so h squared. Well, you have to have a Higgs boson and another Higgs boson, and this basically corresponds to that term. Okay, I haven't proven this, but I'm just telling you what the result is. So this has been already probed by discovering the LHC, and it's related to the mass of the Higgs boson. So because the Higgs boson interacts somehow with protons, and we get this kind of process. So you have proton-proton Higgs, and that already probes that interaction. So perhaps you can already guess what the next one is. So the cubic term is related to the interaction between 1, 2, 3, Higgs bosons. So that's the cubic term. And this is going to be a very challenging process to observe, even in the future. This HL, I should have mentioned that earlier, is a higher data-taking version of the Large Hadron Collider. It would be very challenging to probe it there, but it will be possible to do that at a future experiment. And finally, if you want to probe the quartic, it will be very, very challenging, and this is probably impossible at the high luminosity LHC, at this new version of the LHC. But okay, there are some additional models, extra models that could probe that. And okay, future experiments are also going to be it's going to be very challenging for them to observe this process. I just wanted to mention that we're working on some aspects of this. Okay, but now let me go back to the electroweak phase transition. So the electroweak phase transition, again, is how we ended up from the early universe state, where we had a symmetric potential and a no vacuum expectation value, to the broken phase of this Higgs field, where the potential has a non-zero vacuum expectation value and in this sort of Mexican hat potential. So the nature of this transition is an important open question. We don't know what its order is. So you already know basically some transitions. So the first order transition is an example of a first order transition is the boiling of water. So how does that happen? You have bubbles of vapor being created, and that's basically how you transition from liquid to gas. And this is a first order transition. And then a second order transition is the superfluid transition, and you can also have no transition or crossover. So this is an important open question. How we ended up from the early universe to today, we don't know for sure what the intermediate evolution was. But my claim here is that if we understand that, we may also understand how we got this matter-antimatter asymmetry. And in particular, we can answer the question, was this asymmetry created due to some process that was active during this transition from symmetric to non-symmetric? And this is called electro-weak baryogenesis. Okay. So as I said, the prereq for this to happen, well, I haven't said it yet, but the prerequisite for this to happen is that the order of the transition from early to today, from symmetric to broken, has to be a first order transition. And I just wanted to emphasize the fact that this does not occur within the framework of the standard model. So the transition is not first order in the standard model. So how does a first order transition look like? So how do we get from the early universe state to today through a first order transition? So this is the evolution of the universe as it cools down. So this is basically the same animation I showed, but in one dimension. So as it cools down, at some point, there's a second minimum, but this is higher than the one at the origin. At some point, there will be a critical temperature where the two minima are at the same depth. So if you have a field lying here, then it could also tunnel spontaneously there. Okay, so after that temperature is reached. But when this happens, this can happen at different points in the universe. What happens is you have creation of bubbles of the more stable situation, right? So this is a quantum mechanical phenomenon, so it can happen spontaneously at different parts of the universe, and this creates bubbles. And today, of course, we end up with this potential. Okay, so this is symmetry breaking. So soon after this critical temperature is reached, where the two minima are at the same depth, you get bubbles of the broken phase. So inside these bubbles, you have the broken phase. They're expanding because that's energetically favored, right? So the broken phase is energetically favored, and they're expanding in a sort of plasma of the symmetric phase. So the process which generates matter-antimatter asymmetry could happen at the interface between the bubbles and the symmetric phase. So I want to zoom into that. So I'm not claiming that I'll describe the mechanism, all the details of the mechanism, but I just wanted to give you a flavor. So we have some particles which have this left-handed or right-handed property, fermions, and these interact with the bubble wall. as it is expanding, those arrows are demonstrating the expansion. There are some turns, some interactions on the wall of the bubble that are biasing one-handedness, okay, of these particles. And then there are another class of processes called the sphalerons, which take these left-handed fermions and bias the content in the symmetric phase towards matter. Okay, again, I'm not claiming that there's a full description of the details, but I'm just telling you what the names of these processes are that are involved. However, of course, if you have this process, it can go both ways, right? So you don't have really in the symmetric phase, you don't really have matter-antimatter symmetry. But what can happen is, as the bubble expands, it can absorb this excess matter, and inside this bubble, this process, the Sphalerone processes, are suppressed. So somehow the excess matter that was created in that chain is frozen in, and you have excess matter as compared to antimatter. So, okay, this is something that we asked the question whether you can actually see these processes at colliders. And okay, of course, it's an open question. Okay, so as I mentioned, a first order transition requires new phenomena, and I'm going to discuss one such phenomenon, the simplest, in a second. So, of course, we live here, and one interesting question that we want to ask is, what are the implications of such a mechanism today in our collider experiments? So let's ask, as I said, let me go back to this and just emphasize this point. Okay, now I went too far back. Let me just mention it. A first order transition requires new phenomena, right? So I'm going to discuss the simplest possible phenomenon. So let's take this potential, and we will add a new field, which is a scalar field. So that means it's represented by a number over all of space-time. So S. And this S has no charges, so it means it wouldn't interact with our known universe, except gravitationally, perhaps. However, we'll see in a second that there is some way that it can still interact. So let's write down the potential for this, the general potential. So you can write self-interactions of this field. There's nothing that disallows this. Then you can write such interactions because of some property of the Higgs field that tells us that you can multiply the Higgs field squared by any numbers of any power of this new field. So these are called portal interactions. And the reason they're called portal interactions is because they connect the world of the new scalar S with the world that we live in, which is related to the Higgs boson. So otherwise, if these interactions did not exist, we would never know about this except perhaps gravitationally. And if this singlet field is part of some sector that we don't know about, there's another sort of zoo of particles that we don't know about, doesn't interact except gravitationally with our world, then perhaps this kind of portal interaction could connect our world to this hidden sector, which could also be part of dark matter, or could be all of dark matter. So this is a connection of this kind of model with dark matter. But I won't elaborate too much on it. I just wanted to make the connection here. Okay, so very briefly, what are the consequences experimentally of this? So this is basically the whole potential for the two fields now. Well, you have to break symmetry again, right? We know that the Higgs field has a minimum, non-zero minimum. You have to do the same thing, so you have to go through the same procedure. So that's electro-weak symmetry breaking, BEV, which means vacuum expectation value. So basically this is expanding again, as we did for the Higgs field, expanding above the minimum. But now we also do the same thing for the new singlet. Instead of H, we have chi. So if you do that, you will get the, let's say, potential expanded about the minima, which contains such terms. So the quadratic terms are related to the masses, and maybe you know this, that the mass matrix squared is the second derivative of the potential. So, I've seen this in solid state physics, for example, before. So the second derivative of this potential will be, with respect to h or chi, will not be non-diagonal, right? Because there's that h chi term. So if you want to ask the question, what are the masses of these new particles, you will have to diagonalize this mass matrix, which is basically doing a rotation over the space between the h and chi. So this introduces what is called a mixing angle, theta. So this is the rotation matrix. So basically it goes from this h and chi to an h1, h2. So what is the consequence of that in my experiments is the question. So h1 would be, you can choose h1 to be something like the Higgs boson that we discovered. And h2 is a new scalar resonance. So if you choose theta to be close to 0, what does that mean? It means that this will be close to diagonal, right? So it means that this one would be approximately 1 and this one would be approximately 0. So h1 will pick up whatever interactions h had. So h1 will be approximately h, and h2 will be approximately chi. So h1 will be similar to the Higgs boson that we discovered, but with slightly reduced rates. And h2 will be a new scalar resonance, which absorbs the couplings of the Higgs boson. So these are the primary targets. If you ask the question, this is my model, what will I look for in a collider? These two particles, the Higgs boson, but with reduced production probabilities and a new resonance. So we asked this question for specific future colliders. I just wanted to show you this graph very briefly. This is a color-coded parameter space points that denote, so the color coding basically denotes how sure we are that this is linked to this electro-weak phase transition being first order. I just wanted to highlight the fact that most of these points will be either discovered if they exist or excluded if they don't once we run these experiments. Okay, and I just wanted to say that this is an ongoing process. And okay, this is the final thing I want to discuss. I think it's an important thing in any field. So if you discover something new, some new phenomenon, it's important to be able to understand its origin, right? I mean, that's what we are doing this for. So I found this quote by John von Neumann: "If with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk." So some people actually, ask the question in a paper, and apparently you can, with 4 complex parameters, draw an elephant, and apparently with 5 you can make the elephant also move its trunk. So this was, I was surprised to find this. So in the equivalent question, let's say, is if we discover a new particle, can we actually verify that it is related to the theory that we wrote down? We need to be able to go from the observation to the theory, basically, and this is known as an inverse problem. So experimental observations have to connect to the theoretical parameters. So we asked this question for the specific model that I described. So this is taking 2. So imagine you observe this new particle, H2. Okay, H2 is a new particle, and you observed it in 2 final states. So both of these are functions of 2 parameters of the theory. Okay, so they're different functions of the two parameters. So you can ask the question, okay, if I plot these functions with the width of these bands being the uncertainty in the measurements, can I actually figure out, constrain these 2 parameters, lambda 1, 1, 2, okay, what they are doesn't matter, and sine theta? And the answer is yes. The overlap of those 2 curves roughly will be related to will give you a constraint in these 2 parameters. Okay? Just as an example of this exercise. Okay, and of course, if you want to fully solve this inverse problem in this specific model, you have to look at various processes which are functions of many, let's say, parameters or interactions of these in these processes. So processes such as, let's say, the standard model like Higgs boson, proton-proton to standard model like Higgs boson H1, and new scalar boson H2 will be interesting. And the same goes for 2 new scalars or 3 Higgs bosons and so on. So if you want to figure out what the parameters of the theory were, which means basically these parameters, you have to have enough measurements to go from experimental observations back to these parameters. And this is an ongoing work. Okay, so let me summarize and give you a brief outlook. So this is, by the way, I can't remember what the prompt for this was, but it was again related to Electro-Weak symmetry breaking. So this is also an AI generated image. Okay, so so as I mentioned, we can describe with the standard model and the known particles, we can describe a whole range of interactions, and the precision is actually extraordinary. So I also sort of described briefly what Monte Carlo eventuators are, and that they're basically invaluable tools for communicating the theoretical and experimental results back and forth. And there are many open questions, and I sort of try to motivate the fact that they may be linked via this mechanism of the electroweak phase transition. So the nature of this transition is a question that we want to answer. You know, it's not, it's in itself a very important scientific question. However, if this phase transition was first order, and there's also another qualifier there called strong, but I didn't discuss that. I just wanted to mention that here, you know, in the future, if anybody asks, is this sufficient? First order transition is not sufficient. It has to be also under strong. So if that's the case, then you can generate perhaps matter-antimatter symmetry. And the simplest model that can catalyze such a transition is one where you add a singlet scalar field to the standard model. So future particle colliders potentially can probe this mechanism. So finally, I concluded by saying, if we discover something, we have to figure out, you know, whether it corresponds to the theory that we have by solving the inverse problem. And I discussed some first steps and claim, okay, very briefly, that these multi-scalar processes themselves will be interesting. And also, it's an interesting question whether they can also be discovery channels of some new of this model. Okay, so I think several of these questions, you know, the ones on this slide and on the previous one, merit investigation at the Large Hadron Collider and also at future colliders. For example, you know, the future circular collider as it is known, and also a muon collider. And yeah, that's it. Thank you very much for your attention, and feel free to ask any questions.
Have questions?
Yeah, one quick question. So on slide 35, 36, I think you had a graph of the expectation value of the potential.
Yeah.
Yeah. What experimental observable tells us that we are not at phi equals 0?
Oh, yeah. Sorry, I should have probably. Yeah. So this is linked to the fact that particles have mass. So in the symmetric case, this vacuum expectation value is directly proportional to the mass of particles of fermions, for example. Okay. So let's see. You know, this. I mean, you can see it here. So basically, this is a mass term for electrons, muons, taus, up quarks, down quarks. All the particles that have mass, the fermions that have mass, are proportional to such a term. So if you set phi to 0, all the masses of the known particles would have been 0.
I see.
So in the symmetric phase, all the so yeah, sorry, I should have mentioned that. So in the symmetric phase, all particles are massless. In the broken phase, phi expectation value of phi is non-zero, and all the masses are proportional to that. But of course, there's a proportionality constant in front of, you know, the electron mass is different from the muon mass, but they're all proportional to this value. So that's how, you know, this is constructed to reproduce that actually.
I see. Thank you.
Yeah.
Asti?
Yeah, we're talking about the matter-antimatter asymmetry. Well, certainly in our in our region of the universe, it's mostly matter. How can we be sure that distant, objects aren't antimatter? I mean, because antihydrogen gives off the same radiation as hydrogen.
Yeah. So, okay. So you're asking if we are observing a star somewhere else, how do we know it's not an antimatter star? That's an interesting question. I mean, so you're okay. So there might
because
be,
if you have antimatter,
yeah.
as far as we can tell, there have been experiments actually at CERN on antihydrogen, and as near as they can tell, the radiation, the wavelengths are exactly the same.
Yeah.
So I'm assuming that for other elements, other anti-elements, it will be the same.
Yeah, it would be. It would be. I mean, you need a very elaborate mechanism.
Well, so if we are just looking at photons, how can we tell that distant objects are matter rather than antimatter?
Yeah, it's an interesting question.
I mean, I realize in our neighborhood it's matter.
Yeah.
I've always wondered about that.
Gravitationally as well, it would be exactly the same. So I can't really say. I mean, I don't know. Actually, that's a very good question. So, but somehow there has to be a separating point, right? Because if you have,
well, I mean, the interstellar medium is a pretty good separating medium.
Yeah, that's true. But I mean, there has to be a reason why there's a cluster of antimatter here, completely separated from.
That's a completely separate question.
Yeah. But I don't know if there is any way to probe this. That's a very good question.
I don't know either. I was hoping you would know.
Maybe some of our astrophysics colleagues have some answers to that. I don't know. About this, you imagine that distance are
One thing we don't see galaxy collisions of gigantic antimatter versus matter explosions.
Yeah,
So
that would
it's
be.
not something we observe.
Yeah, the problem is the universe is actually not empty. There's no vacuum. So there's always, everywhere in the universe, there's at least a few atoms per cubic meter.
Yeah.
So if there were a region where you had a mix of matter and antimatter, we would see it. We would see gamma rays coming from certain regions in the universe and we don't.
But also neutrinos, right? So we observe fluxes of neutrino from this
That's a good point.
sources, and we observe fluxes of neutrino or anti-neutrino, so we can distinguish between them, right?
Yeah.
While we
Yeah, that's true.
processes, and then we could figure out like if there is like I don't know supermassive object which emits neutrino or anti-neutrino.
Yeah.
So I have a question and maybe a call to arms. So the question first, can you go back to your slide where you were showing two protons or proton and antiproton colliding and creating a Higgs? You're showing like it's like it was like slide 30 something.
Oh.
Where you're showing like a Higgs interaction of a Higgs and you had either a proton and an antiproton or two protons or something.
Sorry, it's a bit slower. I'm doing with all the transitions. This is the problem with the. Okay, almost there. You're talking about this.
Yes.
Okay,
so as I understand from my colleagues, so they've been dissecting protons or massive bosons and finding out that they're actually complex structures made of huge collections of virtual bosons. And so isn't there like an oversimplification in this particular model? Don't you want to actually represent this as not two protons, but a mass of bosons colliding, and then somehow a single Higgs comes out of it? So where's the magic?
this is oversimplified. So indeed, a proton is a plasma of I don't know if plasma is right, where it's a mix of quarks and gluons, right? A sea of quark and gluon. So that's an oversimplification here, and there's also an oversimplification here because the gluons interact with the Higgs boson via fermions. So there's actually something going on in there too. So there's two oversimplifications, as you said. correctly, there's some, the problem is not fundamental, but also this interaction is not an interaction which occurs at the first order. There's something else in there happening. So the Higgs boson doesn't interact with two gluons directly, but interacts at a higher order in some sense. So there is I can draw it here.
But fundamentally it interacts, so it comes out not of two protons, but out of something inside the proton.
Well, it interacts, so the gluons are picked out of the protons.
Okay.
Then basically what they do is they break into top quarks somehow, and these top quarks close into a loop, and the Higgs boson interacts with the top quarks. So that's what happens basically. But indeed, there's, I just wanted, this is very schematic.
Okay, somehow you did, by making it more complex, it's clearer to me, because I can see the individual things. And then my call to arms, so I said I had a question in call to arms. So I learned most of the physics when I was younger by thinking in terms of geometry, right? Thinking of objects like dimensions or topology or anything like that. And I always thought that the math was just a representation of those geometric objects. And you theorists, you're doing quantum field theory, you drive me crazy because you don't do that. You just go with the mathematics and you say, oh, here's a mass term, and here we have a potential, then it's non-zero. And it drives me crazy because I have a feeling either I'm completely wrong in thinking of the universe in terms of dimensions and topology, or you're not allowing me to visualize what you're doing well enough. Because if you just think in terms of algebra, all I see is a oversimplification or approximation of a real thing, which is this geometric object. I want to see this geometric object. So how can you help me visualize this?
I mean, there is a lot of group theory in particle physics. I don't know if you can visualize that. I mean, there's SU3 times cross SU2 and cross U1. That's what, I mean, you can frame the whole mechanism of electro-weak symmetry breaking in terms of group theory, and I think that's very geometrical.
But what is it? Is it multiple dimensions and you have folded dimensions? How does it work? Do you have loops in dimensions? It can't be just 3 dimensions because the symmetry groups
No, it's not.
call up for more than just the usual 3 dimensions.
Yeah, so there are degrees of freedom and all of this is phrased in that language, but of course it's, but I don't know what you're asking for in terms of dimensions.
All I'm saying is that you do the math and you seem to oversimplify everything just by using the math term. But I want to be able to visualize this. Maybe it's just because if it's multiple dimensions, our brain just cannot go into visualizing 13 or 11 or 10 or whatever dimensions. But you can still do it if you do projections into these, right? So I'm just asking for a way to visualize this other than by giving me math terms.
I mean, the problem is that dimensions are also not dimensions in the same sense as, let's say, space and time, right? There are different kinds of degrees of freedom. I mean, SU2 is similar to...
But then they must represent something. Are they like additional dimensions of time, of space, combinations?
No, they're internal degrees of freedom. Like the electric charge, right, is a U1, which means you can. It's like a rotation on a circle, right? But then what is SU3? It's like a complex 3x3 matrix, right?
It's always some more abstract symmetries.
Okay. Yeah. Think about it and give me something. Otherwise, I'm going to jump into this myself.
I will contain our chair. So I actually have a question about the inverse problem.
Yeah.
So nowadays, people use artificial intelligence to model the application. So how do you think of this as a future of particle physics? Does that mean that the AI will do all this for us in the future?
Well, I think the AI cannot solve the problem if you don't give it enough data to be able to do it. So we need to discover enough, we need to measure enough things such that it becomes a fitting problem that an artificial intelligence machine learning algorithm can solve. Yeah, but it would, I mean, it's definitely it would be an optimization problem, but we still need to figure out enough ways to, and now I'm going fast, enough ways to, we have to feed in enough information, right? So that's the difficult part. And of course, it might be the case that it's not, entirely possible to do that, right? So, going from experimental observation to those parameters is a problem that machine learning could solve. But if you don't have, at least 5 inputs, it cannot fit, right? So that's why I've been trying to find more processes, and that's why I've been thinking about additional final states. Yeah. But I think machine learning is definitely a valuable tool. I mean, we've been using it a little bit. Yeah.
Any more questions?
Yeah, I do have a question actually about the very last slides when you introduced one more scalar as scalar field. So I'm wondering, in general about models, right? So why people like them and what is the criteria of the good models? So there are several lists, and so it obviously has to explain what we observe. It has to be relatively simple. So it has to be elegant. I'm wondering so does the introduction of one more scalar make the situation, the physics more elegant in your opinion? Does it simplify the view on certain things? Or does it overcomplicate it? So,
well, this is the simplest extension you can ever have to the standard model, right? I mean, it's just it's literally the simplest model you can write down beyond the standard model. I don't know if there's anything else that you can consider. Now, whether it is elegant, I'm not sure. I don't think so. Maybe one point about such a model, if you ignore the last term, because that term is just speculation about connections to dark matter. You could have such a model being part of a larger model, which is better motivated, right? So this could, you could have additional stuff that is unrelated to electro-weak biogenesis, let's say, somehow. So, okay, this specific model, I'm not sure if it can be connected to supersymmetric models, but other models with higher representations of scalar fields could be related to the NMSSM or the next to minimal supersymmetric model, and so on. But this is definitely, I'm not claiming this is the most elegant model, but it's a simple model that can achieve this.
Motivated. So let's thank Andreas again.